Now what's this question? This question is asked in GATE 2011. Let the page fault service time be 10 milliseconds. That you know, in a computer with an average memory access time being 20 nanoseconds. So memory access time is 20 nanoseconds and the page fault time is 10 milliseconds. Look at that. So memory access time is nearly, the difference is nearly 1 million times, right? So 1 million times is the difference, half million times to be precise. Now if one page fault is generated for every 10 power 6 memory accesses, which means out of every 10 power 6 times you access the memory, one is going to be the page fault. Then what is the effective time for memory? What is the effective access time for memory? So we know this. Whenever there is a page fault, then we have to do the page service and then the memory access. If there is no page fault, then you can directly access the memory, right? So the formula is going to be like this: effective memory access time is, whenever there is page fault, we have to do the page service. For that time taken is service time, and then you can access the main memory. In case if there is no page fault, then if that is the case, then there is no need of doing any page service. So one interesting thing is, maybe before solving this question, let's see what is the relationship between page fault and then effective memory access time. Let's see that. So now I just want to expand this. Now P into page service time plus PM. See, generally we ignore this M because the M is very less compared to the page service time, but then sometimes M can be considerable compared to the page service time, but in most of the practical scenarios, wherever it is applicable, it is very, very small. But let's assume that it is considerable and I am considering it. Then P minus PM, this is the actual form. It has to be exactly like this if you don't want to leave out anything. Okay, if every stone is turned, then it is going to be the formula. Now these two get cancelled, then what I get is effective memory access time is equal to page service time into the factor P plus M, right? So if you call it as y equal to, you can say this is M x plus C form, isn't it? Now if I draw the graph with x value being the page fault rate and y value being the effective memory access time, the relationship between these two is directly proportional, which means as the page fault increases, effective memory time is going to increase, right? So what is it? If I draw the graph with x being this page fault rate and y being effective memory access time, right? Then what I get is a curve like this, right? So what is this part? This part is C. Why? Because whenever x is 0, at this point x is 0, right? Whenever x is 0, y equal to M, which means even if there is no page fault at all, there has to be at least a minimum M of access time. So that is why M. Is it making sense? See, even if there is no page fault, at least the effective memory access time will be the actual memory access time. In case if there is page fault, then the effective memory access time is going to increase like this, right? So what is the relationship between this effective memory access time and page fault rate? It is directly proportional. So if you have to keep the effective memory access time as little as possible, you should try to keep page fault rate as little as possible. How is that possible? By using better replacement algorithms. Whenever you try to replace an old page with a new page, you should see that this new replacement is not going to hurt the performance. Okay, fine. And now you can do the same thing even with exchanging M and X. You can think of X as page service time and for a constant page rate. So for a constant page fault rate, if you put this here page service time, the same thing will result. So what you get is for the increasing page fault time, the effective memory access time will increase in a directly proportional manner. Got it? Okay, fine. So anyway, you understood this. So you can either use the that formula, or you can use this formula. right? You can either use this formula or you can use this formula, both are same. Now what do you get then? You get what is the memory access time here. So effective memory access time is memory access time. So how much is the memory access time? 20 nanoseconds plus PS. What is page fault rate? So page fault time is 10 milliseconds, isn't it? Yes, 10 milliseconds into page fault rate is 1 out of every 10 power 6 memory access is a page fault, which means 1 by 10 power 6. Then how much is this? This is 20 nanoseconds plus 10 nanoseconds. It is already milli is there, and 10 power 6, if it goes up, it is going to be 10 power minus 6, it is going to be this. So the entire thing is going to be 30 nanoseconds, right? So without any page faults, if the time taken is 20 nanoseconds, with page faults, the time taken is going to be increasing. How much? It is going to increase on average by 10 nanoseconds. Therefore, on average, in order to access memory, the time taken is going to be 30 nanoseconds. Even if the page fault rate is very less. See, 1 in 1 million is very less. 1 in 1 million is negligible. Even if the page fault rate is 1 in 1 million, still we have a substantial increase in the effective memory access time. Why? Because the page fault time is considerable. Even if it is happening only in 1 million time, whenever that happens, it is going to take a lot of time compared to whenever it doesn't happen, right? Fine.